Hi, this is Rob Froney, and I'm here to explain adaptive FIR filters. Here we have an adaptive FIR filter. This is a regular FIR filter with coefficients W sub n. There's actually capital N of these coefficients. Let's write that down here. We have capital N coefficients. This is just a regular FIR filter, and those coefficients, there's capital N of them. You take the input signal x of n right here, and you convolve it with the impulse response, which is consists of W of n times the impulse functions. There's finite impulse response filter, so you convolve discretely x of n with W of n to get the output here, d hat of n. And we have a desired output coming into this whole adaptive system, d of n, to produce an error here, e of n. If we take d of n minus d hat of n, we get the error e of n, and this is like a classical feedback and control system. We feed that error into the update algorithm along with the input, and the update algorithm computes a change in filter coefficients here, w of n. So what we'd like to do next is try and figure out how to do this update algorithm here. The update algorithm will want to minimize this error. In fact, what we'd like to do is probably minimize the squared error, e squared of n. So let's just put that minimize e squared of n, and we're going to do that instead of e of n, because e of n would just go to minus infinity if we minimized it, and the absolute value of e of n is not easy to minimize with calculus. So what we'd like to do is we'd like to figure out what does e of n depend on. Well, it depends on d of n and d hat of n. I mean, e of n is just equal to d of n minus d hat of n, and d hat of n is equal to x of n convolved with w of n, of course. And so let's look at a picture. I'm going to suppose n equals 2. Capital N equals 2. In other words, we have two filter coefficients. So we'll have a two-dimensional thing here. This will be Wn of 0, and this guy right here will be Wn of 1. And if we plot e squared of n here, we could make a contour plot, probably something like this. And maybe it's going down into a hole here. Maybe that's the minimum there. And if we're, suppose we're right here at this specific point at a certain time in our algorithm. And what we'd like to do is we'd like to minimize e squared of n by taking a little step along, by adjusting wn of 1 and wn of 0 a little bit. And we want to take a step that will minimize e squared. And so we'd like to go perpendicular to this this contour line here. You can see that the Wn of 1 is going to be slightly negative, just a little bit like that. And Wn of 0 is also slightly negative. It's more like this here. So we'd like to take this step here, and actually that step is in the direction of negative the gradient of e squared. So we could write a thing like this. We could say delta Wn of k equals minus, I'm going to put minus because I want to go downhill, Mu is my step size parameter. I'm just going to allow myself to change the step size, because if you step too big, you might step right over the hole, you know. So I've got mu, and then I'm going to take times the partial of e squared of n with respect to Wn of k. So that's how we'll change the Wn. And that basically does these little steps like this. And we adjust how far we're stepping with this mu here. So let's see if we can calculate what that derivative is. So I'm going to have delta Wn of k equals minus 2 mu e of n times the partial of e of n with respect to Wn of k. So if you notice here, I'd use the chain rule. Taking the derivative of e squared, I get 2e, the partial of e with respect to Wn of k. So the partial of e with respect to Wn of k is really minus the partial of d hat with respect to Wn of k. And d hat, we said, was the convolution, right? So d hat of n equals this sum, and k equals 0 up to n minus 1 of w sub n of k times x of n minus k, and you just do that sum from k equals 0 to n minus 1, and you get the convolution of w and x. So now if I take the derivative of that, I could write the partial, the partial, I guess is what I want, of d hat of n with respect to hn of k, wn of k, is equal to, well, it's just going to be, if I take the derivative with respect to, suppose k equals equal to 1 here, if I took the derivative of this guy with respect to n of 1, I would only get x of n minus 1. So in general, for the kth one, I'll just get x of n minus k. The other term, the derivative of Wn of 0 with respect to Wn of 1 is 0. So you only get one term every time from the sum. It picks out that term, and the derivative just becomes the coefficient of that term. So now the minus this partial goes in here, and I can write over here that delta Wn of k equals, the minus will cancel this minus, so it'll just be 2 mu, and then I've got e of n, and then I've got x of n minus k. I'll make that parenthesis a little better there. So now if we look at what we can do, our Wn of k right up here is going to be equal to 2 times this error, e of n, which we have right here. Let's make a little, you can see that 2 times this e of n right here, this Wn of k is 2 times that. See, 2 times that times en times, and I just multiply by x of n minus k. So I've got the x coming in here, I've got that info, I've got e, and I can come up with the change in filter coefficients here. Now an application of this might be if we took this x here and we were to run this thing maybe with an unknown filter here. I'll put an unknown filter right here, and I'll put an HUNK of k right there, and then I'll run that guy in over here. Now what will happen is, if this thing is working properly, these Wn of k's will converge to the h unknown of k's here, and this filter will then mimic that filter. So that's just an application of how this might work.